Problem 38. So this problem is adding an initial angle to the projectile motion phenomena. Let me draw a little picture here. This is problem 38. What we're doing is launching a ball, or a ball from the ground into a wall. Although we don't know if it hits yet anyway, whether it hits the wall at its maximum height, like I guess like this, or whether it hits the wall and there's still more height to be gained. But I don't want to have too confusing with drawing, so let's just get rid of that last line. Undo, please. Control Z. Okay. Edit. Undo. No. How many? Holy cow. Anyway. So let's define direction of motion. Up. I'm going to call up positive this time just to screw with your, to change things up a little bit. Plus Freudian slip there. Or was it? We don't know the, yes we do. D is 22 meters, and the height it ends up reaching, we don't know. So it's launched at an angle of 40 degrees, but let's draw a new little, well, the initial velocity is 25 meters per second at 40 degrees. So that initial velocity vector v looks like that. This is v in the x direction, v in the y direction, vy, vx. This is 40 degrees. So we can find these very easily using trig. Vx equals 25 cosine 40, and that, just a quick little review for you, that's because the x component is adjacent to the 40 degree angle, so that's cosine. Don't forget to be in degree mode. This gives you 19.15 meters per second. Whoa, hit the bottom of the tablet there. Yay. In the y direction, we got 25 sine 40, and again, sine is opposite. The y component here is opposite the 40 degree angle. Gives us 16.07 meters per second. So those are our initial velocities in both the x and the y direction. Now let's set up our handy old dandy given column, delta x, vx, t. We only need these three in the x direction for us lazy folk. Is it lazy, or is it efficient, or is it awesome? Velocity final y, a y, t. I think it's awesome. That's exactly what it is. So we're given the x displacement right here, 22 meters. Just stick that right in here. That's the beauty of this table. We figured out the initial x velocity. That's 19.15. I really shouldn't say initial x velocity, because, as we know by now, there is no acceleration in the x direction, so it's the velocity all the time. Speaking of time, we don't know the time, so that's a question mark currently. Question mark. we do know the acceleration. What do we do? Oh, we said down is negative this time, so gotta be careful there. I did that for beneficial purposes only. Definitely not to screw with your minds. Definitely not. This is minus 9.8 meters per second squared. We're given the, well, we found the initial velocity in the y direction. That's the 16.07. And we initially go up, so that's positive 16.07. And that's all we're given in the y direction. So we need 3 givens in the y direction to find any others. We don't have that. We need 2 in the x to find the third. We have that. So that's what we're going to do. Is that's typically what happens is only one of the columns will have enough givens for you to find something. And often that something is time, which you can then stick in the other column because they're the same. So over here we got the equation v equals d over t. Because there's no acceleration, so we got constant speed, and that's 22 over 9 is t, and v equals 19.15. So t, solving a little bit, I'm going to do the whole algebra because I sort of made this messy. T is 22 over 19.15, which is 1.1, I'm going to round up to 5 seconds. So we'll stick that right here, 1.15 seconds, 1.15 seconds. My 5's and s's do look very similar. Sorry about that. What are we looking for? Oh yeah, let's finally do part A. A wants how far above the release point does the ball hit the wall? That's y, right? So we're looking for this. Strangely enough, typically we don't, in the problems in the book and most projectile problems, don't have us looking for the final y velocity. Not all the time, but most of the time we don't have to find this. We're looking for delta y, the height. So delta y is kinematics, right? Yep. Main concepts. V initial in the y direction. T plus 1/2 at squared. We're looking for that, so that stays a variable. This is 16.07 times the time is 1.15 plus 1/2 9.8 negative 9.8. Oh, I almost forgot that. 1.15 squared. And this gives the height as 11.99, should have just rounded to 12 meters. So that's right here, delta y, we can say. Could also stick it over here. Part B wants us to actually, B and C are related. What are the horizontal and vertical components of the velocity as it hits the wall? Horizontal, super straightforward, right? There's no acceleration in the horizontal, so this is always the speed in the x direction. So Vx is 19.15 meters per second. In the y direction, though, part C, we'll need a little bit of kinematics because we have acceleration. So V final in the y direction equals V initial in the y direction plus AT. This is equals 16.07. That's the initial y velocity. Plus negative 9.8 times 1.15, and that equals 4.8 meters per second. So I just got done saying that we most of the time aren't looking for this value, except for the sample problem that I did for you. So take that as you will. Part D. Part D time. Let's have a part D. Alright, so we're trying to find in part D, when the ball hits the wall, has it passed its highest point? So that's why I drew in the beginning, drew as if I didn't know, like I drew it here as if it hit the highest point right at the impact time, but it may do this, still be on the way up, or it may do this, where it's on the way back down. Which is it? What I would do, we know the time, given these initial conditions, we know the time it takes to hit the wall. Let's find the time it would take to reach the maximum height, and that will tell us whether it's, actually we already know this, right? If it was the maximum height, what would this be? I'll give you 17 seconds to think about it. Good, it would be 0, because we've hit the the highest point. So on the way up, the y velocity is slowing down, slowing down, slowing down, stop. Then on the way back down, the y velocity speeds up again. But since this is not 0, we know it's not this. It's either this or this. And technically, we could stop here. We know that since this is positive, we know it must be on the way up. So actually, that's really the way to go. I didn't even think of that. I did it a little bit of a longer way. I found the time, you just using kinematics, and I'll let you do that if you want. But I got a time of 1.64 seconds. Again, setting v final y to 0, I got this time, and then I was like, whoa, this time is bigger than this. So because this is a smaller amount of time, it hasn't had time to reach max height yet, so it must be before maximum height. It must be this one. But I just realized now that's cool. That brings up another cool point. There's usually multiple ways to solve a problem or to think about a problem, and so whichever one comes to your mind first is fine and valid. In this case, the one I did first was a little bit more work. Because we're keeping our signs consistent and defining our signs. Had this been a negative 4.8, we would know it's on the way back down. But because it's positive, we know it's on the way up. And so the answer to our question is no, has not. Invisible ink has not reached highest point yet. Alright, that was a cool problem. The next and last projectile motion problem, problem 46, is a little bit tricky. I had wanted to find a problem that used a similar technique as one of your homework problems, but the book doesn't have one of those that I could see. And so I'm going to use the one that came closest to it, which is problem 46, and then tell you, give you a hint as to how, and this is for problem 47 in your homework. So I'll do 46, and your homework is 47. There's a technique you'll want to use in 47, and I'll show you how to do that. So we'll do that next. Alright, later.